Yeah, I'm still setting up my new office space here, and my equipment is still, well, I'm still figuring it out. All right, so let's watch this. So this is Elias Barenboim. He's a really interesting and brilliant professor at Columbia. When I was doing my PhD at Purdue, he started up his causal inference research there. He's a former student of Pearl. And he's been doing a lot of this initial work in kind of wedding Pearl's framework to causal reinforcement learning. So I'm pretty excited about checking out his work.
I'm glad to be here online today. Thank you for coming. Also, thank you for the organizers, Alessandra and Jerry, for letting me speak in here today. My name is Elias. I'm part of the Causal AI Lab at Columbia University. I'd like to first apologize for my voice. I'm a little bit sick, but I think everything will be fine. Today I'll be sharing what I have been thinking in the last years about causal reinforcement learning of this, or CRL. This is a huge effort in many fronts, and there are many folks helping to realize this vision. This is joint work with the Causal AI Lab and many collaborators. In particular, I will discuss the work here today of the folks here that are on the line: Juan, Sanghak, Janzi, Yuda, Andrew, Dulliger, and Thomas. And I feel very happy and glad and lucky to be able to interact with this amazing team of collaborators. To start, I would like to share an even broader picture that is kind of from a 20,000 feet view, which is the big picture I try to realize in my lab, in which causal RL is a part, and I think it will help to understand the way that I think. And if you are interested in joint effort,
I'm trying to just increase the speed here, but it keeps taking me to this picture-in-picture mode.
Or have questions, or you want to exchange ideas about
all right, I guess we're not increasing the speed.
Some of these topics, including causal RL, obviously. Let me know, since it's a really ambitious, I believe, picture, and it's a generational effort. And my goal here is to convince you that those are important problems, and offer you the opportunity to contribute, but also to ask help. Then I feel that the unique insight we leverage here is quite simple in the lab, albeit powerful, namely that the reality can be decomposed in terms of the causal mechanisms, which we call structural causal model, despite the fact that they are not always observables. And what is important about systems like that they exhibit a feature, or they have a characteristic called autonomy or modularity. You can find in many literature, types of literatures, like in philosophy, economics, and so on, discussions about this feature, which will buy us a lot of power in general AI, machine learning, the data science. We'll follow this picture that, reality exists, and it is modular. And modular in the sense of it can be decomposed as a collection of causal mechanisms. I'll try to make this concrete during the talk. Note that I put here the structure of DNA on purpose. This was to convey the point that this is like is the blueprint of the underlying reality of the underlying system. I usually, personal note here, but I usually joke or partially joke with Yuda Pro, that he discovered the structure of the DNA for intelligence or for AI, and now we are trying to understand its consequence, pretty much in the same way that we have Watson and Crick in 1953 in the Nature paper. Folks were doing molecular biology before for dozens of years, or hundreds, and 100, I should say, and so, and we just know modern molecular biology since this discovery that is kind of an important framing about how to think about these issues, and we are still trying to understand these issues today. It's not that this was done. 1953 was the beginning, and I think the beginning starts with the structural causal model underpinning as this collection of causal mechanisms underpinning the reality. From this view, we have two sides of the coin, or two sides of the structural model. I will call SCM. I use this name many times, and I will define it. First, we like to explain it, explain what's going on underlying the system, which is kind of the goal of science. We like to open nature's black box and explain how things work, or how it could be understood in terms of more elementary and interpretable components. There are books written about this topic. In causal inference, this word has very special meaning and formal meaning. It comes under the different tasks, and there's the rubric such as effect identification and decomposition, bias analysis and fairness, robustness and generalizability, to cite a few. On the other hand, on the other side, you can say, Elias, I couldn't care less about science or explaining something. I'm a pragmatist. I have my company to run. I want to improve the bottom line. I want to generate this better society here for my population if I'm a policymaker. And I just want to decide and improve something. Then this is the other perspective. You could ignore the number one and think about decision making. The task here is how to learn how to intervene in a population or a system using data that is never a perfect match for this population. In machine learning, this comes under the rubric of reinforcement learning as a sequential decision-making center. In the sciences, you can have other names such as randomized controlled trial that is used in the health sciences and so on. For sure, there is some interaction between them. If you understand more about the system, usually this would mean that we can be more surgical, swift, precise, and or accurate, I should say, and to bring about the change that we want. It could be social, it could be economical, and so on. On the other hand, we can
see one thing that I think he's missing here is so robustness and generalizability. If you want to convince reinforcement learning people to adopt causal models, you got to focus on robustness and generalizability. And I think also sample efficiency, the ability to train models with less data. That's going to be a strong motivating point. And it is definitely an aspect of causal modeling, or at least a benefit that causal modeling could bring. But I wish you would, it would mention it here.
If you have some, even if you have low understanding, but we have decision making or interventional capability, we can intervene in the system. We can shake things up, and if you're careful about that, about how deliberate you are, you can learn about the system. This is, after all, even on the science side, this is how we do. We're kind of isolate in a careful way. We can discuss how to do that, but we isolate the system in some way such that we have this capability. We'll be able to discover something, but it's also through the idea of experiments. Now, this is kind of more theoretical part. We can be try to be more. There's also the implications of that. We are interested about applications, education, and software. In terms of applications, there are kind of two big buckets, I would say, that are not. This is not a partition. On the left side, we have data science. We're trying to do principal inferences from large data collections. And what I mean by principal, we would like to be able to have this stamp saying scientific, and we could discuss what scientific means
Speed up. This guy's going slow.
in the context. And on the other hand, you have the problem of AI that we're trying to learn principles and tools for designing robust and adaptable learning systems. This will be kind of the topic here today. We are focused on AI machine learning, and in particular in the reinforcement learning problem. Today, I'll be talking about causal RL in particular. Then the first question is like, what is causal RL? And to answer these questions, I'd like to make two observations. First, that reinforcement learning is quite awesome at handling sample complexity, and also the credit assignment problem. Given that we have this kind of delayed rewards that you take action now, and something will just come up, have these kind of long time trajectories, and the delay will come pretty late or very far from now. Then I think this is where it shines through. And on the other hand, we know that causal inference is pretty great or awesome as well in leveraging structural invariances across settings, conditions, and environments. Maybe there's a word missing here, environments. Then those are two disciplines that kind of evolved independently, virtually independently, very clear interactions of cross development. And the obvious question here is,
So this is an interesting dichotomy here. Sample complexity and credit assignment. So credit assignment, I assume he means here that's figuring out which actions lead to good, delayed, cumulative rewards. Sample complexity, I imagine, means the complexity of the data, or perhaps dimensionality. Say, for example, images from a computer game, for example. And I mean, reinforcement learning is good at many things, these among them, this being among them. And of course, this is levering structural invariances across settings and conditions. What this means is that if you have a causal model, it's the assumptions that you're making about that model will be consistent across different data sets that you might see, insofar as that data is relevant to the model. Because if it's a causal model, then it's reflecting actual causal mechanisms in the real world. So it's interesting, but of course, causal inference has different things that you could say are good about it. So choosing these three features to emphasize as being the strength of two different areas of research, that's an interesting choice.
Can we have the best of both worlds? I'll be upfront and say yes, given that I'm enthusiastic about the topic. And the question is how, obviously. And the solution is very simple. It's a simple equation. Causal RL is equal to CI, causal inference plus RL, reinforcement learning. It sounds like a joke, supposedly, but that's the fact. More seriously, what we are trying to do, or our goal, is to provide or to develop in reality a cohesive framework that takes the advantages of the capabilities of both formalisms into account, and I would say from first principles. We don't want to have a hack here. We're the best machine learning AI community here in the world. Then from first principles, such that so as to allow us to develop the next generation of AI systems. That's quite ambitious goal. For sure, you have people in, there's a whole spectrum here. I have been giving not exactly this talk, but variations and about the particular tasks. And we have the spectrum, but it oscillates between a lot of excitement, say, wow, that's pretty cool, usually from the younger people, and for our spectrum. But people are like, wow, this is, once they understand, they say, wow, this is exactly what we need, and how can you help, and let's try to realize this goal. On the other hand, you have the people that is more some type of resistance from both sides, from the CI side and from the RL side. Some people can be more conservative. Usually my experience, because they're not understanding what the other person on the other side is saying. It's obvious as well. Usually you get resistance, as Max Planck says, science progresses from funeral to funeral. But I would say that the goal here of the tutorial is to try to bridge this gap and offer this common language that we can understand what are the challenges, or what are the new challenges, and what we're trying to accomplish. Then the outline here, in order to realize this vision, the outline of the talk will be, I try to ground the equation that I gave before. And here's the outline. I first start with foundations of CRL, of causal reinforcement learning. I will give an introduction to structural causal models, SCMs, the pro-causal hierarchy, the PCH. I'll explain what this means, or the ladder of causation, as it's called. And I'll ground how these things connect to a result called causal hierarchy theorem, CHT. A partial joke with the CLT. I think it plays a similar important central role to causal inference. This is kind of basic fundamental material. Then we'll try to understand the current methods in RL and CI through this lens, through the CRL lens that we're trying to develop. Then this is the first part. It will be abstract in some way, but completely necessary in order to understand what are the new challenges and opportunities of causal RL, of CRL. I will roughly try to do 60 minutes each. They asked me to do 30 times 4. I think it fits more naturally, and they said it's totally fine. I appreciate Alessandra and Jerry. I'll do 60-60, approximately. Now, the goal here, one thing I'll say, the goal is to introduce the main ideas, principles, and tasks. As I said, not focus on the implementation details. As I mentioned, just said, having think about this issue for some time, visit the different places, my understanding is like people is talking over each other. Then the idea is, let's try to ground what are the foundations, what are the principles, and what is really the task that we're solving. And then the rest will follow. It may take 1 month, 2 months, 6 months, maybe 1 year, as some of the theorems and papers or more. Emphasize this other aspect today. Now, with this textbook definition, this is an environment. Then it means that you cut a line, and there is something external and something that is not external, and there is the need to decide what to do. It's a learning problem without the full specification of the system. We're not doing planning, but most of the many problems that I'll talk here also, even if you're doing planning, they will appear. But I'll try to emphasize this other aspect today. Now, with this textbook definition, this is the textbook picture. If you're teaching the RL 101, in the first 10 minutes, this is the kind of picture that you give, or a variation of that. We have the agent on the left side, and the agent in reality is something that is parameterized. Then we have this collection of parameters theta, and on the right-hand side, we have the environment. then we're interacting with the external environment, and then it means that there is the agent. Now the agent is perceiving, then there is this thing called the context of states, some type of stimuli that comes in, and then the agent do some type of processing and decides to do something and commits to this action. It do the variable, let's say x is equal to some value x, and then the environment gives it back the reward about what's the effect of the action. The environment is the one that is evaluating. Now here it just receives the feedback in the forms of rewards. The agent's utility is defined as a reward function. And the goal here is much to learn how to act so as to maximize some expected utility or expected rewards. The general idea here is like a unifying theme that we have in AI. That is we would like to develop rational agents, and we have this link that's a classic result about rationality and maximizing expected utility.
So I'm just trying to blast through all this
or maximize expected rewards.
intro to RL stuff. Now I want to get to the meat.
Oh, that's good. Now, it's late here at the moment, but now I was thinking about how to make the smallest possible change in this textbook figure so that I could convey what I believe CRL is about. This is the picture that I could come up with. In the left side, now we have the agent. Sorry, let's start with the right. In the right side, we have the environment, but the environment here is given by something called this structural causal model. The environment is this collection of causal mechanisms that I will define in 1 second. In the left-hand side, we have the agent. And the agent is this collection of parameter thetas, but now we have the causal graph. That will be defined as well formally. And also in the picture, I usually think that I don't like the word. I think it's overloaded. The last word here is like there are different types of interactions. Perhaps they can passively be connected with the environment. As we say, there's observational, or through observations. It can be actively interacting through interventions, or it could be kind of doing some type of introspection or retrospection, or using its imagination about this environment that's called counterfactuals, which I will develop here soon. Now, just to make clear what I said.
Okay, so this is interesting. Let's go back a little bit. All right, so there's some underlying structural causal model. So a structural causal model is an explicit representation of a causal data generating process. And when you have a structural causal model, it describes completely the causal mechanics of the system. And it's a limited modeling framework. It can't express every kind of causality, but that's a philosophical point of argument, but generally speaking, this is saying that the environment is operating according to some ground truth structural causal model, and what you have is a causal graph and some parameters, so essentially a causal graphical model that captures the same distribution as the structural causal model. And that our action space is going to expand. So he's going to take this word and break it up into 3 kinds of things that you can do. One is observe, intervene, and the other is imagine. So kind of reason counterfactually. Well, although I don't really like that because actions change the environment. Observing and counterfactually imagining, they don't actually change the actual environment. They might change an imagined. The counterfactual reasoning could change an imagined environment. So let's see where he goes with this.
Be defined as well formally. And also in the picture, I usually think that I don't like the word. I think it's overloaded. I think the best word here is like there are different types of interactions. Perhaps they can passively be connected with the environment. As we say, there's observational, or through observations. It can be actively interacting through interventions, or it could be kind of doing some type of introspection or retrospection, or using its imagination about this environment that's called counterfactuals, which I will develop here soon. Now, just to make clear what I said, I would like to be as crisp as I can. The 2 key observations, this is all what I said that I want to add to the picture. Number 1, if you're trying to move RL to CRL. Number 1, the environment and the agent will be tied through the pair SCM-M and causal graph G. SCM in the side, in the environmental side, causal graph in the agent's mind.
So if you're just tuning in, I'm looking at this ICML tutorial done by Elias Barenboim, just done last year, on causal reinforcement learning. So he's now extending this definition of RL where you have an agent interacting with environments through an action, there's some kind of reward. What he's doing now is expanding that to have a causal definition. So we have the environment that's given by some ground truth causal model, in this case a structural causal model. We have a causal diagram, which is the agent's, I suppose, assumptions about the causal dependency of of the environment, and some probabilistic parameters that encode some probability distributions that follow that graph. And let's see here, the environment and the agent will be tied together. The pair, so there's some pairing between these two things. I guess we're going to assume that G is a match for M. So G is a graph, M is a model, but M and G will entail the same underlying joint probability. No, more than that, that M captures the structure of G, or that G rather captures the structure of M, and we'll define different types of actions to avoid ambiguity. Okay.
Number two, we define different types of actions, of interactions, which we try to avoid ambiguity, that were given by this PCH, by the pro-causal hierarchy. That again, I will define following one step. But that's at least the picture that I would like you to have so far. Two things, two bullets, the pair SCM and graph G, and the other one is the PCH is mediating there about how these things interact. I forgot about this one. Let's define and understand number one, that is the pair M and G. Number two, that is the PCH. Now starting with structural causal model and causal graphs. Let's get into it. I'd like to start with some kind of intuition behind what is a structural causal model that we are trying to represent a data generating model. There are different types of generative models of the environment or nature and so on. There are different types of generative models. This special one, we'll talk one and we define semantics and so, but it's a process-based approach. Try to give an example in the context of drug, assuming that we're trying to relate or to understand the relationship between drug consumption or intake and headache. Now here we have the process-based approach in which drug is a function, or there is this mechanism that is.
And he's calling this a process. The SEM is a process-based model. I've read about process models as one kind of model of causality. I'm curious if he's thinking about the same literature that I'm thinking of. But anyway, so we have drug being some kind of deterministic function of age and a random noise variable, headache, a deterministic function of drug and age, and some other noise variable.
Giving value to the drug. Then this mechanism f sub d take as input the age of the person. Depending on the age group, people is taking drug in different ways. There are different propensities to take drug. And also there is this variable u sub d, u of unobserved. And this is all other variables in the universe that generates direct variations to the variable drug that are not age. Second mechanism of the variable headache. Headache is a function of, or gets its value based on whether the person got the drug or not, depending on the age of the person, and u sub h. What is u sub h? U sub h are all possible variables in the universe that are not drug and age. Now, there is also a graphical, you could have a graphical counterpart of that. This is the graph that we have. For simplicity here, instead of drug, headache, and age, I'm calling XYZ. Just to make, I usually interchangeably, but I started thinking from the specific name. And on purpose here, I didn't pick an example in robotics or some other team because I'm trying to say that CRL is much more general than that. Meaning we don't need to attach to robotics, even though there is awesome stuff going on, including people that is thinking or doing causal stuff or starting to do causal stuff. But I would like to be less committal. But soon this will be just an action, this will be outcome, and this will be a set of covariates. Now, what is the meaning of this? Here we have the start having the processes that are related to this causal mechanisms encoding reality, and here we have a causal graph. What is the causal graph? This is not a BaseNet, this is not an MRF, this is not any other model. This is a causal graph. What is the meaning or the semantics of the causal graph? The arrows here, if the variable participates in the mechanism of the other, like, age participates or gives values to headache through this f sub h, then you add the arrow from age to headache, from z to y. If drug participates in the mechanism of headache, then you add the arrow from drug to headache.
Okay.
If age participates in the mechanism of
so now you're showing you how to go back
D,
from the
then you arrow from z to x. That's this is a encoder. There's some type of loss of information. Note here, by the way, one thing that I didn't say. This f sub d here could be a crazy function. It could be a linear function that is very easy to think about, or it could be a completely crazy one, even that exhibits, chaotic behaviors, or it could be complete anything. I'm not instantiated here in the slide. I'm trying to leave it open to any possible function in the universe. While here, but it is instantiated in the particular problem. While here, we don't have clue of the functions. We're kind of have some type of coercion here. Anyhow, from a process that is going on through in this way, we can sample from it, and we get what is called a probability. We got data. Let's say that we get a probability distribution, P of Z. There is some discussion, but I will skip about the P and the P hat. I'm assuming I'll get back to that at some point, I believe. We can sample from the process that is in the left side, which gives rise to this observational distribution among the observables P of Z, X, and Y.
What does that do?
Now, we are here today, not that and we can do statistics or some type of AI machine learning on top of that. But we are here today because we are trying to understand about what the heck is causality and how this relates to interventions or to reinforcement learning. Now, The idea of intervention is like how the system will react when it undergoes some change. And what's the change here? The change is like for example, we come from outside as an external agent, or agent, I should say, and we decide to change the modus operandi about how the drugs are being assigned, and now we just make drug is equal to yes. Then we decide to submit our population to have access to this drug. Let's say that is a vaccine to the coronavirus. And this is the operation here. You are replacing or rewriting the original mechanism with some other, in this case, is a constant yes. What happens when you do this intervention? The mechanism of the other variables, given that you just did the intervention on drug, remains invariant. That's where we start getting this autonomy or modularity. Now, observation here, I'm just talking about the intervention, yes, but this, when you are running a randomized control study, there is some kind of random coin there that is deciding the value of the drug. Still, it is not the same mechanism as people get the drug usually, but it's a different one. It's randomized, but it's a different one. It's not a constant, but it's a different one than F sub D. You can have more sophisticated policies, as you'll be interested, that is a pi of age. Depending on the age group, we decide to give drug with a different likelihood or different probability. Then that is different, let's say, about how people are choosing by themselves the drug. This is F sub D, there's a different argument, and so on. Then there is some subtleties about when you have conditional policies, not for our discussion here. You can check this beautiful work by Juan with me about some of these subtleties, and I think that's enough. Here, at least for the sake of argument, everything will be fine if I just put the yes here, in order I can round things up. Now, there's also the graphical counterpart of this operation that is happening in the mechanism level. And here, as you can think, the Z is no longer, the F sub D is no longer active, then Z no longer affect X. Then there is just a yes there. Then you kind of, this is where the arrow removal appears. Oops. Here, there is an alternative notation for that. For sure, you can sample from a distribution like that. If you're able to contrive a situation in the world in which you'll be like that, like the picture in the right side bottom, now you can sample.
Right, so again, watching this tutorial on causal reinforcement learning, let's see what he's done here. He's introduced this mutilated graph. We have G, which was derived from the actual true structural causal model that underpins the environment. And now we have an intervention where setting X to yes, which will break influence from his parents. And okay, and then we have some notation here. So this is probability of Z given X equals yes, probability of Y given do X equals S, which is equal to this. Okay, so we'll just, right now he's just explaining causal reinforcement learning. He's recasting it using causal semantics. But at this point, he's kind of moved away from reinforcement learning at this point and is now looking at a toy model. See, here's how I would have done this differently. One of my experiences working with people with a reinforcement learning background is that they look at examples like this, age, drug, and headache, and they're thinking like, listen, I work on reinforcement learning. Why am I looking at this toy model? Everything in reinforcement learning is super complicated. I don't think you have much to say, at least about my problem. So I think if, not to criticize Elias here, I think if it were me, I would have presented this as perhaps a model from a OpenAI gym example. Maybe I'll write something up like that.
From this process, and this gives rise to something called the experimental or the interventional distribution P of Z, comma Y given do X is equal to yes. You also can have alternative notation that P of Z sub X is equal to yes, Y sub X is equal to yes. I use this other type of counterfactuals that I'll mention later on. We'll stick with the new notation for now. Now, again, as I mentioned before, alluded to before, usually we are talking about the drug will be in general any decision, the outcome will be, Y will be any outcome, that could be the reward, and the Z will be the set of features. And I use these terms consistent with the notation that we have in causal inference. Now, challenge here is that, which I'll be back many times, usually you don't observe these mechanisms. Sometimes you can observe the causal graph that is already discoursening, and many times you cannot do the intervention. Then usually we have data that is coming from the left-hand side, and we are trying to do the inference in the right-hand side, as if you have done the intervention without doing it. That's a classic. Then from saying the system, passively, we would like to make a statement as if you are doing the intervention in the system. If you are able to do this type of very hard type of prediction of the effects of our interventions, then you can be surgical, and eventually you can avoid experimentation, side effects, it can be safer, and so on. I'll come back to that again. Now, let me just try to generalize this idea of interventions and equations or mechanisms.
All right, let me restate that because it sounded like it was actually pretty important. So was he saying that so oftentimes you don't have this seeing to doing this graphic is not particularly clear, but you see the graph, or at least you have a graph where you assume the graph is true. The underlying structural causal model, I think he's assuming that you don't know what it is. I mean, based on the papers that I read, I mean, you could assume that you know it. But I think what we're going to say here is that maybe we don't know. We just think we have a graph that kind of matches the underlying model or the underlying data journaling process. And if you have the graph and you have the parameters, then you could, for example, simulate from this mutilated graph. But I think reinforcement learning is going to say perhaps that you don't know the parameters. I think that's how he's going to cast it, and that you want to. That's how I would cast it. And that sort of goal of reinforcement learning is to learn those parameters of this graph.
Saying the system, passively, we would like to make sure you're doing the intervention in the system. If you are able to do this type of very hard type of prediction of the effects of our interventions, then you can be surgical, and eventually you can avoid experimentation, side effects, it can be safer, and so on. I'll come back to that again. Now, let me just try to generalize this idea of interventions and equations or mechanisms describing some type of mechanics, and define a little bit more formally a structural causal model, which is a tuple with 4 components, V, U, F, and P of U. The set V is the set of endogenous and from side. Endogenous variables or observable variables, V1, V2, Vn. In this case, in the previous example, V1 could be D, the drug, and V2 could be the if you have headache or not, and V3 could be the age. We also have the set U, that is the set of outside exogenous variables in the systems. U was unobserved, and you have many of those.
So this is just how you specify a structural causal model.
F, that are functions that determines the value of the endogenous variable. For each endogenous VI, we have this function Fi that listens, as Paul is used a metaphor in the book of Y, but in general, that listens to the PAI, a set of observable variables called parents, and the set of UI called exogenous variables. So far, I was describing essentially Newtonian physics or some kind of deterministic system. Whenever you decide to have a cut and you put some variables outside and you decide to analyze others like V, there is some uncertainty about what's going on in the description outside the box, outside the model, that then there is a probability distribution, P of U, that we're sprinkling there, summarizing the kind of initial conditions of the state of the universe outside. Then this is what we have. It turns out that systems like that admits or has an axiomatic characterization that is well understood by in this work by Halpern in 98 and a model.
So let's see if I can explain this again. So again, this is how you specify a structural causal model. You have some variables like you'd see in a DAG. Exogenous variables, it's not a class of variables, but they're the input noise. What a structural causal model does is it takes these exogenous variables and sets each endogenous variable as a deterministic function defined here of its parents. So here it's each endogenous variable V sub I is a deterministic function of its parents in the graph and an exogenous variable, and that all of the exogenous variables are independent. That's important. And let's see, and that we also specify some kind of prior distribution or probability distribution over all of the exogenous variables.
The work by Gales and Pro, Halpern's logician in Cornell is doing kind of awesome work, and Gales was Yuda's student working in this particular problem. Essentially any result that you derive today can be traced back to this one if you want to go to assembly code. I'm more interested, at least for now, in the following observation. Once you have SCM, a specific instantiated of this object, this implies this thing that we're calling the pro-causal hierarchy, or what is called the PCH, usually causal hierarchy, I call pro-causal hierarchy. in honor of him. Now I would like to understand a little bit more or open up the box about the PCH. For the sake of context, this is the main metaphor, the main topic, I would say, of the Book of Why, if you read. It was also called that, the ladder of causation. I think it's in chapter 2, if my memory is right. As I said, we used to call in the lab the causal hierarchy, and this is different names. This will help to ground our discussion. Don't forget the picture that we had before, in which we have this, I promised, three building blocks. The connection between G and M. I talk abstractly and give the math what they mean. That G is a coarsening of M. And now I also said that the point number 2 was about these different, not actions, but the different types of interactions, which is given by the PCH, in which I would like to talk a little bit more. If you haven't read the book, this is just a review. It will be okay. If you haven't read the book, sorry, if you did read the book, that's fine, that's great. I will try to review and ground in the way that I'm thinking about it, that not exactly the same. It's mathematically the same. And if you haven't read the book, that's fine. You can read the book. It's kind of a very good book, entertaining and good and nicely done. But it will be okay that I'll give you the basics here. Now, what is this PCH, Elias, that we're talking a lot? Please tell me. I'll describe this level, a symbol, typical activity, typical question, example. The first layer that we have is L1, that is called, in the book is called rung, they usually call layers. The first layer is called associational, L1. Symbolically is described by words like P of Y given X, as we have there. Is related to the activity of seeing. How would seeing X is equal to X change my belief in the variable Y? What does a symptom tell us about the disease? If you want to find a counterpart in modern machine learning, this is related to studied for many years in statistics and in other fields, but very successful in machine learning. This comes under the rubric of supervised or unsupervised learning. There's many formulas and a huge amount of theory about how to evaluate expressions like that, P of Y given X, such as decision trees, a long time, Bayes nets, regression, hierarchical models, neural nets. Challenge here, why you have been studying this problem for a long time, I get this question, is like nowadays you operate with this Y given X. X is the set of features and Y is the label, for example, but this can be in the order of hundreds of thousand dimensions, of millions even nowadays, that I'm aware of. Then this is really difficult, both in terms of computational complexity and in terms of sample complexity, because you don't have all the combinations. Then whatever, this is the reason this is such a challenging problem. Now, on the other hand, you have another layer that is called the interventional layer, L2. Symbolically, you write like that, P of Y given do X, given that we observe C, or context or state, is related to the activity of doing. What if I do X? What if I take the aspirin? Will my headache be cured? That's nice. In machine learning, as you can hint, this is very related to the problem of reinforcement learning. That is why we are here today. There's different formalisms that can handle that. I'm just listing some of them. A causal-based net, a CBN is called, MDP, a Markov decision process, and there are others. Now we have the third layer, that is the counterfactual layer. I'll skip here the symbol for 1 second, L3. Is related to this activity on imagination, introspection, retrospection, Y type of questions. What if I had acted differently? Was it the aspirin that cured my headache? Now, I took, let's say, now let's try to parse here. I took the aspirin, that is X prime, and now I'm cured. And I'm wondering, would I be sick, that is Y, had I not taken the aspirin, that is X?
So here's a better reinforcement learning characterization of the counterfactual, which is to say that I watched an agent do an action and they got this reward. What reward would they have gotten had they done a different action? See, that's that counterfactual policy evaluation. I think that is really an important use case for applying causal modeling to reinforcement learning. This interventional case, of course, this is just what happens if I do this action. And this is essential because what I've shown previously is that when you're actually doing an action and it's changing the environment, it's changing the states, and that is an intervention problem. And if you're trying to, and so like the transition function, that core element of the Bellman equation, which is the main equation of reinforcement learning, requires this do notation to actually really make any sense. And once we write the Bellman equation in these terms, then things start to make a lot more sense, and we understand why, for example, reinforcement learning suffers from robustness and generalization issues, is because we're trying to learn a causal or an intervention distribution, but we actually fail a bit in this and learn an associational distribution.
Then we have this counter, the factual world. In the factual world, I did take it, and I'm okay now. Not really, I'm a little bit sick, but I'm okay now. Let's say X prime is took the drug, and Y prime is, I'm okay. And I'm wondering what would have happened had I not taken it. Then it's a heavy load here. There's no counterpart really in the machine learning literature. This is model, and you can ask me questions, even though there are claims here and there, but we can have a discussion. But roughly, there is no, not well studied yet. There's huge amount of work in the CI field about that, but still much more to be done. The formalism that we have for this kind of problems is a structural model. Now, I would like to make a note here about why is this a hierarchy, and the hierarchy means that there is something about this is, if you keep going up in the hierarchy, this is flipped. But if you go from L1 to L2, L3, this is from the last detail from something that's a correlation between X and Y that we are trying to leverage here, between the image that we are trying to pick up the signals with some outcome of some label, to be more detailed about the counterfactual. That is a very detailed description of the system. It may sound...
This makes sense. So what he's saying here is that, so here you can just do this, like if you wanted to predict some value of some variable given another variable, you just need, regression or enough information about the system to fit a regression line, or neural nets, as an example of a nonlinear regression line. For intervention distribution, you need the graph. You need that graph object that he introduced in the previous step. And then for this imagination introspection, then you're going to need a structural causal model. Although there are some broad assumptions that you can make about the system. I'm actually going to take some notes about that, because I feel like I say this a lot, and I don't. Hopefully you can't see my notebook here. I don't want you to see that. But just putting a little note in my notebook, my little inbox. I find myself explaining this quite a bit, that you can get some counterfactual inferences without a structural causal model, so long as you have the graph and you have some assumptions about the broad class of structural causal models that you're working with. Why is everything so supersized on my computer right now? 1 second. Oh, let me just play while I type. Sorry.
Sound a little bit, but I would say it may sound a little bit abstract for now. Stay with me, don't be nervous that I will use examples of layer 3 later on, but I think we can get the feeling that this is kind of different task already about this collision of the worlds. And this is, by the way, very related to the problems of blame and responsibility, credit assignment, fairness, interpretability, all falls there in L3. Still not explored. In other words, I think you should study. But anyhow, it forms a hierarchy in this sense, and I would like to ground a little bit in terms of the amount of information that we have about the environment, of the true environment, the true causal mechanism. Then try to expand or ground a little bit, given my expectation here that we understand roughly that those are different types of things. And I would like to explain a little bit more this containment that we have, what we call the CHT, as a partial joke, as I think I already mentioned about the CLT, which is a central element in the causal inference literature. It's believed to hold, by the way, I should mention historically, for a long time by folks such as Yuda Pro himself, me. One of the reasons I'm very excited even came to the US because of a result like that. It was just proven in generality recently. Let me read it here. Given that SCM implies the PCH, and we can show that or defines or induces the PCH, we can show the following result. With CHT, with respect to Lebesgue measure over some type of technical conditions here over the SCMs, the subset in which any PCH collapse, I quoted here because I didn't define, is measure 0. Let me try to try to put it with words. In other words, for almost any SCM that you could get, usually you don't know which one is your environment. This is your unobserved. But for almost any SCM that you get, the PCH doesn't collapse in the sense that layers of the hierarchy remains distinct. Then you don't have this type of situation that maybe you do some, the idea is like you have these notions of observations and notions of interventions. It seems to be different if you read the book of Wire, if you think about that, or about imagination as well. Maybe in some world they could be the same. We just don't know how to reduce one to the other. Here, in some way, we are saying no, it's not true. One is strictly more powerful than the other. Then there is things that statements. Better way to say a statement about the world that L2 is making that L1 doesn't know.
Right. So what this is a measure theory proof, but it's basically saying that the separation of rungs on that ladder of causality, that in this causal hierarchy, is there's no overlap, right? So it's that if that the kinds of state that L3 is strictly more expressive than L2, that an expression that can be that requires L3 to express is there's never an occasion where level 2 intervention. So in other words, a counterfactual, retrospective, imagine style question. There's never a situation where L2 is sufficient to answer the full scope of those questions. Similarly with L1. So this is really important for reinforcement learning people to understand. Rich Sutton wrote in his essay, the bitter lesson. What he wrote in that essay is that it's not really useful to kind of bring in domain knowledge because computational methods will always, if you can solve something with, well, rather what he's arguing is that don't worry about domain knowledge because eventually you'll be able to brute force it with computation. So once the computation gets cheap enough or accessible enough. And what this proof shows is that actually if you have observational data, you can't brute force an interventional or a counterfactual query.
About it, or under specifies.
Not with just a bunch of computing data, in other words.
Corollary here, to answer questions at layer I about a certain type of interaction, one needs knowledge from layer I or above. Let me try to understand, try to connect here what we're saying. I said the following: each SCM that is nicely shown here induces this hierarchy, that is, these different types of interactions, different notions in the world about observing, about intervening, about thinking, and so on. Now, that's all good and nice and sounds beautiful. Then the question here is like, why is this non-trivial then? Why is causal inference non-trivial? I can just compute everything from the SCM that I have. And one of the most common questions, by the way, that I get. But it's very interesting thought, or a dream, I would say, because in fact this is not true. Things are not so easy, unfortunately, exactly because as I wrote here in the title, the SCMs are almost never observable. Now, even though this is important, even though there is a SCM there is a collection of mechanisms there, we don't fully observe it. We just observe some fragments eventually that is in the layers, not all in general. Now, I have to say here, this is almost never. We almost, as the title say here, SCM is almost never observable. For sure, there is exceptions, such as in physics, in chemistry, sometimes in biology. The very science in these fields is trying to learn about this mechanism. Then they are kind of zooming in a very detailed level. Sometimes it takes 100 years or 250 to move from one theory of physics to another. But in reality, they are serious, and this is the kind of phenomena.
This is actually why I really love working in biochemistry for causal problems, because there you can get the SCM, usually in the form of a set of differential equations. So I wrote a paper where we took a kind of ODE specification, or rather a stochastic differential equation specification of a model, and cast it as a SCM, and we're able to produce some useful, imagination questions about cells. But I think generally outside of the natural sciences, you don't get the SCM.
They are analyzing some type of phenomena that allows them to do that in some way. It's enough for now. But I will argue that most of the settings that we are interested in embedding AI and in which humans are involved is practically impossible to get the description of the SCM. The humans are in the loop. They are unpredictable. There is some kind of chaotic component there, and essentially the problem, the complex phenomena is involved. Then and there are social interactions, and there are many other types of interactions. And there is no way that we can isolate the system in some way that things are so clean. Then this is a first world citizen here. We are acknowledging that we cannot get that. This is an important point. Now, what's the deal, Elias? Then what are you talking? I'm talking that suppose that you have an agent that is embedded in this environment, and the agent keeps some time observing what's going on in the world. Then it's getting this layer one type of data through observations. Again, this is similar to my picture before. I'm just grounded with the PCH. The agent is getting observations, and now the agents want to infer about what it should do in the system. Now, is it possible to use the data from this layer one in order to make a statement about layer two? Now, unfortunately, the answer is no. I put a bar there. Why? We just discussed. This is the CHT. CHT is saying that we cannot move across the layers because there is more information. Layer one underdetermines layer two. That's the theorem. Then not possible. Now the question here is like, I mentioned there's given the unobservability of the SCM, together with the CHT, it seems that no inference is possible within this PCH. We cannot get any information from the PCH, given that I cannot observe this guy, and we have this CHT proof. Then the question is, what can you do? This is kind of strong negative result, and the idea is like, this is the very motivation why you like to study something about the SCM. And these things is what we call these structural constraints, and a graph is nothing more than a collection of structural constraints.
So
there are different classes of graphs, I would say, or different.
So he's assuming he's casting reinforcement learning as a problem where you don't see the SCM, but you do see the graph that kind of underpins the SCM. So that for a given graph, there's a whole, in other words, SCMs have a graph structure. It is, so if you went back to that definition of an SCM, we're at 45, let's see here. Ladder stuff, here we go. Come on, YouTube. I don't know why it's so hard for YouTube to do this kind of thing. Anyway, what I was saying was that when you specify an SCM, there's an underlying graph structure. That graph is the graph that we're going to work with when we do reinforcement learning. And that one, the graph, we can assume it based on domain knowledge. We might be able to learn it from observational data, at least up to an equivalence class of graphs. But the SCM we can't learn from data. We can only rely on an experiment on domain knowledge. And in most reinforcement learning settings, we don't have that domain knowledge, because if we did, we probably wouldn't have to use reinforcement learning in the first place. So, man, I hate when it certainly does not make sense that Google. All right, here we go. So you see here that that each node here in the SCM is a deterministic function of its parents in a graph. And so you have a graph here, and that's the graph that we're going to work with, I think. Well, I know in this reinforcement learning problem as he's characterized it. And so let's see. I imagine what we're going to do is try to learn some parameters that entail, allow us to kind of, with the graph, we can get as far as seeing and doing. We can't get the counterfactuals, but I think that there is some results that show that under certain assumptions about the SCM, ones that you might be able to make using domain knowledge, you might be able to get some counterfactual queries, some pretty good, some important ones, but we'll let Elias talk a little bit more here.
I'm banded, or you have an MDP, or have a POMDP. This is a template. Even though people thinking algorithmically, if you open up the algorithm, you are able to extract the graph. This is exactly the assumptions that they are making about the environment. And have been popping out there, papers here and there doing that, but it's a template. We can do knowledge engineering, that maybe you have some extra information about the environment. I don't know, in economics, people is able to elicit instrumental variables. Then perhaps you can leverage that. It imposes some type of constraints in this. It is encoding some type of constraints about the underlying SCM. For sure, number two is more general than one, because one is just it's just that we would like to believe that the word conform is kind of cookie cutter in some sense. But anyhow, then there is the third one, that if you want to test your model, or even if you want to learn from scratch, if you want to build a baby Einstein, that you want to keep evolving, don't want to hard code the code there, this is called the causal discovery. In other words, that's kind of the motivation. Let me try to put the pieces together, because there are many conceptual blocks here that I mentioned, and I think it's good to summarize. The environment or the mechanisms can be modeled as an SCM. The SMM, that is the specific environment eventually that you're embedding in your system, is rarely observable. Still, each SCM can be probed through qualitatively different types of interactions of distributions, that is the PCH, observations, interventions, and counterfactuals. And not only probe, but the types of interactions, but also modes of reasoning. But there is this way of interacting with nature. But now it comes the CHT that says that for almost n SCM, lower layers, let's say layer Li, underdetermines higher layers, layer Li plus one or above. These delimits or in some way constraints what an agent can infer based on the different types of interactions and data it has with the environment. For concreteness, I already give this example. From passively observing the environment, that is L1 type of data, it cannot infer how to act. From intervening in the environment, all possible interventions, and you do L2 kind of data, it can't infer how things would have been had she acted different. That is a L3 type of statement. And I'll just give you the example, you can show that. Then the causal graph, G, is a surrogate of this underlying system, and in reality of the structural invariances that I encode. The causal graph is a surrogate of the structural invariances that underlie the system, underline M. Now, okay, that's good.
Okay, so I'm going to stop it there. I'm going to work through this particular workshop over the next few Fridays. But yeah, that is Barenboim's introduction to causal reinforcement learning, and we'll plow through the rest of this workshop as we go forward. So thanks for tuning in today, and talk to you soon.